We're Team 7 from the University of Nevada, Reno. Today we're going to tell you about our fluidized bed coffee roaster that we built for Particle Technology. I'm Richard Mantre.
I'm Derek Satterfield.
Ali Oliva.
And Nikolai Cox.
Jumping right into the project, the team had 4 main goals that they wanted to achieve throughout this project. The first, of course, was we built a working fluidized bed that roasted coffee. The second goal was to make the perfect cup of coffee, which one of our teammates drank and enjoyed. The third was to characterize the fluidization, which we found was a Geldart D classification, giving us spouting flow. And finally, we wanted to define the scale-up parameters so that we could then take this onto industry and see how it would work. Now, while everyone knows the basics that go into coffee roasting, of course, raw coffee beans and heat create cooked coffee beans. But let's really take a second and go back in time and look at the history of coffee making so we can really appreciate how far the developments have come. The first ideas in coffee making were relatively primitive, and they mainly involved holding a spoon over an open flame in the attempt to cook the coffee beans. As time went on, technology increased and they were able to move the coffee beans around to get a more homogeneous roast. Jumping forward to the 19th century, the commercialization of coffee production became a very important idea that sadly did not take on as well due to most people still cooking coffee in their homes. However, with the industrialization era, the commercialization of coffee production became widespread throughout. Moving forward to the modern era, fluidized bed coffee roasting is the cutting-edge method and accepted by most roasters. Now that we've covered the background on coffee, let's talk about a fluidized bed. So from the figure from Rhodes et al., you can see that there are 4 major classifications that fluidization falls under, being C, A, B, D in that order. The reason for this non-alphabetical order is that the Geldart C classification stands for cohesive, which do not generally tend to fluidize very well. In addition, from the figure, you can see that these classifications are based on a different density between the particle and the fluid, as well as the particle size, meaning that based on what you are running in your fluidized bed becomes very important in how well your bed is going to fluidize. Another desired condition with the fluidized bed is the smooth fluidization as seen in figure 7.4, also from Rhodes et al. You can see that in figure B, the particles are just barely apart, indicating smooth fluidization. Due to the size of coffee beans, however, our fluidized bed is classified as a Geldart D, meaning that we would end up with a spouting fluidized bed, as seen on the left figure on this slide. Instead of smooth fluidization where the particles barely separate, there's more of a tumbling effect seen in our fluidized bed. Now that we have some background on a fluidized bed coffee roaster, let's talk about the development. Of course, the first step was to go shopping and buy all the parts necessary to put together this project. As we can see, we ended up with a heat gun, a bottle, some rolled up metal, pipe clamps, all of that, which finally came together to be our first iteration, where we had originally put it within the metal casing for more protection. However, this later proved to be more cumbersome and we later on eliminated it. However, without the metal casing, this now proved to be an insulation issue as well as a temperature issue. Thus, to eliminate that, the team wrapped the fluidized bed in insulation so as to protect both the team as well as keep heat in the fluidized bed. In addition to all the other parameters, the size of the bed was very important, so multiple bottles were used. Looking into experimental, we can see with a smaller bottle, thus a smaller diameter overall, the bed is more fluidized, thus showing that the beans will go further up into the column, which was an important consideration when looking into the flow rate. In addition, this video is about 2 seconds shorter than the other one, proving that those beans are cooked a little bit faster. Moving on to the bigger diameter bottle, throughout the video you can see that these beans do not quite go as far up into the column as the previous video, although they still fluidize further on into the video, showing that the mass loss is mainly fluid and that this does increase the fluidization height. The next design consideration was for the pressure drop, which was an important metric in understanding the correlation between pressure drop and mass loss for the fluidized bed. Furthermore, to connect to the outlet, we used a manometer made with tubing and water and food coloring to be able to measure the pressure drop, because with a manometer you can use the height differential to see the pressure in inches of water. The final design consideration was some chicken wire that was bent up to prevent the coffee beans from falling down into the roaster and thus catching fire, which proved to be a significant issue in the design of this roaster.
To ensure that the reactor operated properly, a lot of initial calculations were made. XP represents the diameter of coffee bean. Rho P represents the density of coffee bean, roasted. Rho G is the density of the gas. Mu G is the viscosity of air. And F is the fraction of powder less than 45 micrometers, which in our case is 0. From the previously mentioned parameters, we calculated the minimum fluidization velocity based on this empirical relationship as seen, UMF, and from that we extrapolated the minimum volumetric flow rate needed by the fan to actually fluidize the bed. These calculations were used to ensure that the parts bought for the reactor were actually able to fluidize the bed.
From this project, there were many deliverables that came out. The first being a fluidized bed coffee roaster using a heat gun and everything mentioned prior. The second being the ability to take raw coffee beans and later have roasted coffee beans, which could be used to make coffee.
On average, we found that around 20% of the mass was lost when making a dark roast. As you can see, as mass is lost by the beans from roasting, pressure drop decreases. With these results, we are able to numerically quantify when each roast happened in our reactor. This enabled us to make light, medium, and dark roasts consistently. Each of these roasts can be seen in the next slide.
One of the biggest benefits of using a fluidized bed coffee roaster is the versatility and the scale-up associated. As you can see, we went from raw coffee to a dark roast. On the left, you can see the raw coffee beans that have not experienced any heat, the light roast, which experienced heat for about 3 minutes, medium roast being about 3.5 minutes, and finally our dark roast, which was roasted for the longest of about 4 to 4.5 minutes. What this really comes down to is that each of these roasts only has a difference of about 30 seconds, meaning that there's a lot of versatility in ways that this can be done to get the best roast possible. So, in summary, we hope you take away from this video that fluidized bed coffee roasters are relatively simple to make. In addition to that, you can very much control the darkness of your roast based on how long you roast the coffee beans for. And finally, that if you do decide to build your own, some important considerations would be the volumetric flow rate of your heat gun as well as the bed diameter.